Okay. Let's, why am I not getting any sound out of this?
That's what I was thinking.
Hello, hello, hello. Hello, 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 hello. Check, check.
I just put my don't know because I thought that would be so bad.
Hello?
What? Return tree is better than I don't know? I guess so, yeah.
Hello? Is the microphone working? No.
I was thinking about that.
Check, check, check. Okay. All right, so I'm trying to figure out why, if I can convince the microphone to actually work. So I'm, for at least a few minutes, I'm just going to need to yell. Solutions for the midterm are up. All the stuff in gray is stuff that we did not expect you to write down, but we're looking for the stuff that's written in black. You know, by far the hardest question, both in terms of the length of the answer and the insight needed to solve it, was problem 2, as expected. For people who are curious, the idea was that we're supposed to consider sort of the state of a particular person to be not just their location, but also location at a time. Okay, the microphone just doesn't work. Interesting. If at some point you decide you can't hear me, please raise your hand, and I'll try to speak up. So the idea is to create several different copies of each node that represent a particular fountain at a particular hour. And then you have edges that represent transitions, which have 2 types. One is at hour I go through a gate, and the other is at hour I do not go through a gate, but I just stand here. Going through a gate, that edge has capacity 1 because only one person can go through the gate, go through that gate at that time. But the capacity of the edges where you stand still is infinite because there are no constraints on how many people can stand around the fountain. And then it's a maximum flow from Earth at time 0 to Fillory at time h. This is going to be an interesting one to grade because I've already heard 3 alternate solutions, which may or may not be correct, but because I didn't ask you to write down a proof, that means I have to figure out whether they're correct or not. Here's the proof if you care, right? And then I suspect that people are going to do reasonably well on problem 3, reasonably well on problem 4, because that's just add a source, add a target, disjoint paths. And then problem 1, at least the first couple of parts, I'm expecting people to do reasonably well, and then the last part, there's a couple of opportunities here for partial credit that I think most people will get some credit for the last part of D, and some people will get most of the points for the last part of D. So my guess, partly based on just looking at the exam in hindsight, based on experience, and partly based on comments from other students that have talked to me after the exam, I'm guessing the average on this one is going to be somewhere in the low to mid 20s, somewhere between 21 to 24 out of 40. I do want to remind everyone that in the end, everything is going to be curved. So if, for example, problem 2 ends up being a bloodbath, it'll be a bloodbath for everybody, which means everybody will be soaked in red, but still everybody's grade will adjust because the grade cutoffs will adjust. If it really looks awful, and unfortunately this does happen occasionally, that I ask an exam question where the most common answer is I don't know, then we just throw that question away, and people who actually submitted the correct or partially correct answers will get those points as extra credit. So yes, the exam was harder by design. Still, I think reasonable, but we'll see when everything clears up. So let's. Are there any other questions about midterm 2 that I might ask you read the solutions before you ask the question, but if you have especially admin questions about midterm 2, I'm happy to answer them now. Yeah.
So the bit of bug on my expectation, question 1, is that propagated down the chain through the C's. Is that factored into grading, or?
Yeah, we'll factor that into the grading. Okay. So we're now 3/4 of the way through the course. So the course is divided topically into 4 chunks. The first chunk we talked about dynamic programming. The second chunk we talked about randomized algorithms. Ultimately, mostly randomized data structures, but still randomization. The third chunk, we talked about flows and cuts and generalizations up to linear programming. All of these things have been about proving that problems can be solved quickly. The fourth part of the class is going to be primarily about proving that problems cannot be solved quickly, and what to do about that fact. Okay, so the literally million-dollar question that I'm going to be talking about for the next few lectures is this, innocuous string of 5 symbols. Does P equal NP? How many of you have not heard this question before? Anyone who's taken 374 heard at least something about what NP is. It's kind of a free-floating idea of what it means. But just let me nail this down. So formally, P and NP are sets of languages. If we remember from 374, we talked about various kinds of machines, DFAs, NFAs, Turing machines, possibly some form of push-down automata, either in 374 or 421, accepting a set of languages, or accepting a language, which is just a set of strings. But thinking about this in terms of algorithms, it's probably a little bit more natural to think of a language as a yes-no question. Is this array sorted? Is this string of parentheses balanced? Does the following Python program halt on all inputs? Okay. So we can, if we think in terms of those, if that formalism, P is the set of yes-no questions that can be answered in time polynomial in the input size. Okay, so for example, is this array sorted? You can answer this in linear time, where n is the size of the array, the number of elements, by a simple for loop. For I equals 1 to n minus 1, if a sub I is bigger than a sub I plus 1, return false. If you get through the entire for loop, return true. So that running time is, in this case, a polynomial of degree 1 in this variable n, which is the length of the input. If you really want to be formal about this, I have to say array size in bits, and then the actual time, the running time becomes a little bit more complicated. But because we're really only interested in things either being polynomial or not polynomial, we can fuzz that distinction about whether we want to measure in terms of bits or in terms of number of words. And we can think of the integers as each being stored in a single word in memory. The differences are not important enough to open up that particular can of worms most of the time. Another question might be, is there a flow? Actually, can all 42 physical kids get from Earth to Fillory in 24 hours? This question can be solved in time. This is from the solution to the midterm question. Here, the running time is being reported as a more complicated function of several different parameters. I'm going to assume here. Well, we have to think how are these different parameters given? So you can imagine that the graph is given, say, as an adjacency list. And here, this is h. This is a constant. So really, the h can vanish from the big O notation in that case. And then it's not too hard to see that this is at most the square of the number of bits you need to write down to describe the graph. Okay, so this is polynomial. On the other hand, if I specify this number h as part of the input, I only need log h bits to write that down. And then this is no longer a polynomial running time. Right? We saw this effect when we were talking about Ford-Fulkerson. Ford-Fulkerson running on integer inputs isn't a polynomial time algorithm because the running time might be exponential in the number of input bits. Most of the time, that particular issue doesn't raise its ugly head. But every so often, when you have a number that's provided in the input and that same number shows up in the running time, you have to pay attention. Okay. The other half of this equation that we need to understand is NP. This stands for non-deterministic polynomial time. It does not stand for not polynomial. Okay. It's non-deterministic polynomial time. In terms of the kinds of things we did in 374, this means it's a yes-no question that can be solved in polynomial time by a machine that is allowed to make guesses and always gets them right when the answer is yes. A better way to say that is these are yes-no problems where any yes instance can be verified in polynomial time. Okay? So I have some yes-no question. For example, is this array sorted? I can convince you in polynomial time that a sorted array is in fact sorted by saying, go run that linear time algorithm. Or I could say, look, these two things are in order, those two things are in order, those two things are in order, those two things are in order. I could run it myself, and that is the definition of sorted. So you should be convinced now. But maybe something that is not so clear how you would solve it from scratch, for example, is does this graph have a Hamiltonian cycle? So a Hamiltonian cycle is a cycle that visits every vertex in the graph exactly once. Now, we don't know whether this problem is in P. We do not know whether there is a polynomial time algorithm which, given an arbitrary graph, can determine, 100% of the time correctly whether or not that that graph has a Hamiltonian cycle. On the other hand, if I want to convince you that a graph has a Hamiltonian cycle, how could I do that in polynomial time? I just give you the description of the Hamiltonian cycle. I say, well, you could start at vertex 1, and then go to vertex 7, and then go to vertex 42, and then go to vertex 17. And to sanity check me, you'd have to verify that, in fact, every transition that I'm naming is an edge in the original graph that I'm following in the right direction if the graph is directed. And that I start and I end at the right place, and I didn't leave any vertices out. So there's a little bit of sanity check bookkeeping to do. But I can prove to you that a graph has a Hamiltonian cycle in a way that allows you to check that proof quickly. This proof is the set of non-deterministic guesses made in the formal definition of non-determinism, where in any transition I have two states I could choose from, and I pick one according to clairvoyance. That really is, I think, more intuitively captured by saying, I have a short proof, which you can verify. Okay? Now, there is an important asymmetry here. How could I convince you that a graph does not have a Hamiltonian cycle? Good answer. I don't know either. Nobody knows. The best, honestly, nearly the best answer we have is try all possible permutations of the vertices, and for each one, check if that's a Hamiltonian cycle. That isn't a polynomial time algorithm. There are n factorial different permutations of a graph that has n vertices. So that doesn't give me a way of verifying a no answer quickly. Right? That's fine. NP only requires that yes answers. If the answer is yes, I can convince you in polynomial time. Okay? So if the answer is yes, I just show me the cycle. And if the answer is no, I don't know what to do. Okay? Now, everything that you can solve from scratch in polynomial time and always get the right answer is in this class of problems. Right? If I want to know whether the minimum spanning tree in a certain graph has weight less than 1,000. I want to convince you of that in polynomial time. I will say, just compute the minimum spanning tree already. Why are you bothering me? right? And if the answer is yes, you'll figure that out in polynomial time. Now, it's also true if the answer is no, you'll figure that out in polynomial time. But, okay, fine. All right. So the million-dollar question is every problem in NP also in P? For every problem where I can verify a yes answer quickly, is there an algorithm that can decide yes or no quickly? Now, in one sense, the answer is, of course not. Everybody knows that it's easier to check my solutions to the midterm than it is to take the midterm. Right? But that's the question that we actually don't know. We don't know, we don't have a theorem that says that these two families of decision problems or families of languages are different. So in 2000, the Clay Mathematics Institute put down a list of the 7 most important open problems in mathematics. So this is a 100-year later update from a list of 30-something problems that David Hilbert proposed at the International Congress of Mathematicians in 1903, I think it was. And that list of Hilbert problems kind of drove mathematics research for many decades. So the Clay Math Institute said, okay, we're not going to be as ambitious as Hilbert. We're not going to come up with dozens of these. We're only going to come up with 7. This was number 1. And the reason it's number 1 is because if the answer is yes, P equals NP, what that says is anything where there's a short proof, there's an easy way to discover it. In other words, all of mathematics just became trivial. Right? So I think it's actually fair to say this is not only the most important open question in theoretical computer science, it's not only the most important open question in computer science, but it is in fact the most important open question in science. So the Clay Math Institute will give you $1 million. This is chump change. This is literally, we will name it the Your Name Here Mathematics Institute. Yes, you will get a Turing Award and an Abel Prize and probably a Nobel Prize in economics. Because, resolving it either way, 5 different computer science departments will name their universities after you. We just don't know. We don't know. And not only do we not know how to prove this, we don't really have any idea of how we might prove this. And in fact, we can prove that we really don't have any idea how to prove this. And what I mean is, roughly every 15 years since 1970s, when this problem was first formalized, there have been a whole bunch of attacks along similar lines. So in the 1970s, people said, oh, if we can we figured out that we can do linear programming in polynomial time. Maybe we just need to find the right linear programming formulation of NP hard problems, and that will, that if we just figure out the right formulation, that'll solve the problem. And then somebody said, no, you cannot find the right formulation. There's a formal proof that the traveling salesman problem in particular, this Hamiltonian cycle problem, has no concise linear programming formulation. So, okay, the only idea we had is now dead. And that happened again and again and again. So there's one exception. There's one guy at the University of Chicago, Caton Momoli, who believes that there's a potential approach that might lead to a resolution of this problem using some heavy-duty tools from algebraic geometry. he estimates it'll probably take somewhere between 75 and 100 years to work out the details, assuming it works at all. And that's the best hope we have. Nevertheless, 3 times a year, somebody proves that P equals NP, and 3 times a year, somebody proves that P is not equal to NP. And for some reason, these 2 groups of people never seem to talk to each other. So I want to give you a particular example of a problem that's in NP, and that is in some formal sense the worst possible problem in NP. Meaning if you can figure this one out, you've got everything. Okay? So I'm going to start with a problem that is kind of obviously hard. Okay? So I want you to imagine that you're looking at a box that has a light bulb glued onto the top, and it's got N toggle switches, all currently pointed up, sitting in the front. 0, 1, 0, 1, 0, 1, 0, 1, and so on. And a nice man in a bright red suit, with slightly pointy ears and potentially tail, says, hey, you know what? If you can turn on that light bulb, I'll give you $1 billion. But you know, if you agree to take this bet and you can't turn on the light bulb before you die, I take your soul to hell. Don't take the bet, right? In this circumstance, you're not allowed to look inside the box. The box is opaque. In this case, you can actually prove that the only strategy you could possibly hope to do to decide whether it's possible to turn on the light bulb at all is to try all 2 to the n possible settings for the switches. You just sit there with a little binary counter and flip the switches until you die. And then at the very last minute you say, I don't think it can be done, and Satan walks over and goes, flip, 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 flip. Light bulb comes on, says, welcome to hell. Okay? So, of course, we know this, so we're not going to take the bet. Okay? And so, in fact, you say, you know what? I recognize you. You're wearing the bright red suit. It kind of gives it away. So, of course, I don't trust you. I'm not going to take the bet. And then Satan says, okay, fine. Good. You don't trust me. Because after all, I could change the inside of the box. You don't actually know whether there's anything in there at all. So I'm going to make the box out of glass. So you can actually look inside and you can see all the wires and how they connect to each other. And you can, you know, I'll let you take the box apart. I'll give you the plans to the box. I'll let you build your own box. I'll just hand you the plans. Okay, and the plans consist of, well, there's a toggle switch and there's another toggle switch. It's a simple Boolean logic circuit. Okay, you've got AND gates, you've got OR gates, and you've got inverters. And the graph that this defines, you can think of all the edges as being directed from the inputs to the output. You can quickly check this graph is a DAG, topological sort. And Satan says, you know what? You go on, you come back and tell me yes or no, and we'll check it together. I'm gonna head out. I'm busy. I've got 4 billion other people to drag to hell. Okay. And now the question is, should you still take the bet? Is there a fast way of checking, given an arbitrary Boolean circuit, whether or not there's a setting of the inputs that makes the light bulb turn on? Now, this is a problem that's in NP. I can convince you that there is a setting of the switches that makes the light bulb turn on by walking over and setting the switches. And in fact, if you have the plans for the circuit, I can just tell you, okay, the setting that makes the light bulb go on is 011011110011011, and you can trace through the circuit, again using depth first search, topological sort, to figure out what the output value is and see whether it's actually a 0 or 1 in linear time. Okay. So this problem is called circuit satisfiability, which is, given a Boolean circuit, are there inputs that produce the output 1? Right? I can convince you the answer is yes quickly by just telling you, try these inputs. You can grind through. There's an obvious algorithm which takes time, something like 2 to the n times n. This is brute force, which is, well, I've got 2 to the n possible inputs. For each one, I need to trace the value through the circuit. I can do that in time linear in the overall description complexity of the graph. So I get something like this. The best algorithm known for this problem is a little bit faster, but only a little bit. Okay? So, no, you don't want to take this bet. Unless you want to bet that you're smarter than, every mathematician in the last 100 years. Okay? Now, what's interesting about this problem is that if you could solve the circuit satisfiability problem in polynomial time, improving this, this slightly less than brute force algorithm to something small like n to the 5 million, then every other problem in NP would also have a polynomial time solution. Okay. This is a theorem that was originally proved by Leonid Levin in the Soviet Union in the late 60s, and independently by Steve Cook, then an assistant professor at Berkeley in the early 1970s. It was known forever as Cook's theorem because no one could tell what was going on behind the Iron Curtain. Interestingly, Cook did not get tenure. That was a little embarrassing for Berkeley. Even now, that's a little embarrassing for Berkeley. So he just moved from being an assistant professor at Berkeley to being a full professor at the University of Toronto, where he's been ever since. And 5 years later, he won the Turing Award. Levin didn't win the Turing Award because he was still behind the Iron Curtain, even though the historical record now suggests that Levin actually had the idea first. So what the Cook-Levin, following standard practice in theoretical computer science, I'm putting them in alphabetical order, theorem, in modern language is circuit sat is NP hard. And what this phrase NP hard means is if circuit sat can be solved in polynomial time, then P equals NP. Okay. So a problem is NP hard if a polynomial time algorithm for that problem implies P equals NP. This resolution of this 50-year-old open question, and that will, among other things, get you $1 million if you win, if you actually prove it, either true or false. Okay. Now, actually proving the Cook-Levin theorem is a little bit out of the scope of this class. I can, in a few minutes, try to give you some intuition about how this works. The main idea is formally all this is happening not with computers and not with algorithms written in carefully structured English. Formally, this is all happening with Turing machines. And what you can think of, a non-deterministic Turing machine as, well, you've got a work tape, you've got your finite state control, you've got your input tape, and you've got your proof tape. Okay? And the idea is you provide, initially the work tape is empty, the input comes in from the user, and when I say, I can verify something is yes, I'm in polynomial time, it means there exists a string that I could put on the proof tape to make this Turing machine accept in polynomial time. So what you would actually do then is build a circuit that simulates this Turing machine. And the way that you do that is you have wires that carry a signal that is on if there's a 1 on the work tape at a particular spot at a particular time, and 0 if there's a spot on the work tape that's 0 at a particular point at a particular time. And then you encode transitions between these wires based on the state transitions inside the Turing machine. Right, so you say, okay, here's the Turing machine tape at time t equals 0. Here's the Turing machine tape at time t equals 1. Here's the Turing machine tape at time t equals 2. And going between these layers, you have some complicated Boolean formula stuff, which encode the state transitions of the finite state control of the Turing machine. So if you imagine sort of taking all of these, there's a polynomial number of these layers because I want the running time of the algorithm. Sorry, I want the Turing machine to halt after a polynomial number of steps. Okay, so I'm going to imagine, this is some sort of black box. The inputs that come in are over here, the contents of the proof tape, and over here, the contents of the input, and down here, either a 1 or a 0. And then this is all encoded by the Turing machine itself. And then you say, okay, here's a problem that I want to solve. I want to verify whether it's true. Once you actually get the input, you fix the input values. And then what you're asking is there a proof string, the remaining inputs which I haven't specified, which I can feed into this complicated Boolean circuit that will make the output be 1, indicating that that Turing machine would have accepted this input as a proof that the other input satisfies the problem that you're interested in. So for example, if I wanted to prove that a given graph, I could build a Turing machine that verifies that a graph has a Hamiltonian cycle. The left side of the input, I would feed in the graph, and then the right side would say, is there a proof? And over here I would put in a description of what I claim to be a Hamiltonian cycle. And that Turing machine would output 1 if it really is, and 0 if it isn't. So if the answer for a particular input is yes, then there is a proof. In other words, there is an input to this big Boolean circuit that will be accepted, meaning the light bulb will go on. That's the basic intuition. Given a non-deterministic polynomial time algorithm for anything in NP, I can transform it into a Boolean circuit. And that Boolean circuit is satisfiable if and only if the instance of the other problem that I started with is a good one. Yeah?
So when they show the complexity graph where you
Yeah.
And then NP hard is a parabola that partially intersects
Sure.
NP circle.
So there's some set inclusions here. This is the Mickey Mouse diagram. Okay.
So how come any NP hard problem being solved would mean that P equals NP?
That's the definition of NP hard.
It's like,
That is the definition of NP hard. A problem is NP hard if a polynomial time algorithm for that problem implies P equals NP. So the reason why circuit sat is hard is if there were a polynomial time algorithm to check, here's this big nasty circuit that I built out of my Hamiltonian cycle algorithm. Is there an input that makes the light bulb go off? If that problem can be solved in polynomial time, I've just described a polynomial time algorithm to solve the Hamiltonian cycle problem. Step 1, build this giant circuit. Step 2, pass it to the circuit sat algorithm. Step 3, profit. No missing ... You're just done. Right? Okay. So this is the definition of NP hard. Now, some NP hard problems are also in NP. Those problems are called NP complete. That is probably the last time you will hear me, sorry, the second to last time you will hear me utter the phrase NP complete. Because it doesn't matter. What's interesting about these difficult problems is that they're hard. The existence of an algorithm to magically check if you can guess the proof is not really that interesting because we don't have magic genies that will tell us the proof. What's interesting about these things is that they're hard. And so the basic idea now, once we have this one problem, here is circuit sat. Once we've identified one problem in this class, we could solve circuit sat, we could solve anything. The interesting thing is that we can leverage this to show that lots of other problems are NP hard. And if we believe P is not equal to NP as a sort of physical law, 50 years of ignorance are enough to convince us that they're probably not the same set, P and NP. There probably are hard, actual problems that are really hard. So if we imagine that we take P is not equal to NP as an axiom or as a physical law, then NP hardness means no polynomial time algorithm. There is no way to solve the problem quickly. Okay. Now, sometime back in the 1980s, there was a conversation between, I believe it was Richard Karp, who was one of the people who drove the theory of NP completeness, who did get tenure at Berkeley, and Richard Feynman, who was a bongo-playing womanizer who also did physics. He was, a really gigantic figure in 20th century physics. Famous for his ability to solve problems. So there's something called the Feynman method for solving problems, which is 3 steps. Step 1, write down the problem carefully. Step 2, think really hard. Step 3, write down the answer. So Feynman took one look at the statement of the problem and said, of course they're different. And it apparently took like several afternoons over drinks to finally convince him that, no, there really is something to prove here. Because it's so blatantly obvious that you can't solve every problem from scratch just because you can verify the answer afterwards, even if you are Richard Feynman, that Feynman, there's nothing to prove. I mean, it's sort of clear. Physicists are incredibly good at intuition, and most of the time their intuition is spot on. Alas, they're not known for their formalism. And so eventually I think Feynman was turned around and said, okay, it's a boring problem, but okay. But we don't think it's a boring problem. Sorry, when I say we, I mean I. I think it's an incredibly frustrating problem because it is obvious what the answer is, but still completely opaque how one would actually go about proving it. Okay, so once we've started along the idea that we've identified something up here in this NP hard cloud, namely circuit set, I want to leverage this into proving that other things are NP hard, which at least morally is the same as a proof that they cannot be solved in polynomial time. And so the first one of these that I'm going to look at is something called formula satisfiability. I'm just going to really show just an example on the screen here. Okay, so this is a Boolean circuit. I'd love to know whether it's satisfiable or not, whether I can plug in values at the front and get a 1 out at the end. So the formula satisfiability problem says the input is a Boolean formula, something written in the language of Boolean algebra, where I have variables that are connected by various operators like equals and not and or and possibly implies, and these if and only if, and these can be nested arbitrarily. Just get some arbitrary expression in this algebra of over Boolean variables. And the question is, given an expression like this one, can I assign values to the variables that will make this expression come out with the value true? Okay, now hopefully it's not too hard to see just from the example, thinking about it just a little bit, that this formula satisfiability problem is really just another version of the circuit satisfiability problem. They're really almost identical, in the sense that if I'm given a circuit, I can transform it into an equivalent formula that just describes the circuit. And in some sense what I'm saying is, how would you be given a circuit in the first place? You wouldn't be given this drawing, you'd be given some formal specification that says, well, here I have an AND gate and it's connected to this OR gate and that NOT gate on the inputs and this AND gate on the outputs. But one particular way that you might describe a circuit is by giving the wires names. So I'm going to name the input wires X1 through X whatever. I'm going to name the output wires Z. And I'm going to name all the intermediate wires Y1 through Y whatever, in this case 6. And then for every one of my gates, I'm going to write down an equation that must hold for those variables. So this gate here says X1 and X4 is equal to Y1. Okay, there it is. And Y2 is equal to the negation of X4 because of this gate. And Y3 is the AND of X3 and Y2, or here it is, this AND gate. And then I just write down these equations, one for every gate. I connect them together with ANDs, and then at the very, very end of the formula, I'm going to have this clause that just says, oh, and Z is true. The light bulb is on. Okay. And I claim that there are inputs to this circuit that force Z to be true if and only if there are values for these variables that force the entire expression to be true. So what I've done is an example of a reduction. This is exactly the same as like reducing, can I get a bunch of people from Earth to Fillory to maximum flow? I've reduced circuit sat to formula sat. And like any other reduction, I need to give a proof. And that proof is likely to have two stages. So in the first stage, if I'm given, suppose I can satisfy the circuit, meaning there's inputs that make the output true, then I can push the values all the way through and find corresponding values for all of the wires. And then by brute force, I can verify that by assigning each variable the same value on the corresponding wire in the original circuit, that I've made the output formula from the reduction equal to true. And then going the other direction, if there's a set of variable assignments that make this formula come out to be true, then I can pull those variable assignments back to values that are on these wires. Those are going to be consistent with the semantics of AND gates and OR gates because of each of these sub-expressions having to be true. And because that the only way to get an AND of a bunch of things to be true is for each individual one to be true, I get the semantics of the gates from these clauses and the fact that the light bulb is on from the last clause. And so the X's give me a satisfying assignment for the original circuit. Okay. So there's an easy transformation that moreover can be done in polynomial time. And this means that if I had a polynomial time algorithm for formula sat, then this reduction would give me a polynomial time algorithm for circuit sat. But I don't believe there's a polynomial time algorithm for circuit sat because if there were, where's my $1 million? So I've just proved, essentially by using a proof by contradiction, there is no polynomial time algorithm for formula sat. All right, now the picture that I want to draw looks like this. The argument goes as follows. Imagine, for the sake of argument, that there is a magical rainbow algorithm that solves formula sat in polynomial time. I'm doing a proof by contradiction, so the first thing I do is assume the negation of the thing I'm actually trying to prove, which is that sat is NP hard. So assume, no, sat can be solved quickly. So I'm going to build around this a polynomial time algorithm for circuit sat. And a polynomial time algorithm for circuit sat takes in a Boolean circuit as input. In linear time, transcribes it into a Boolean formula. That Boolean formula gets fed into the magical rainbow sat algorithm, and that magical algorithm either outputs true or false. And then I need to prove that if the sat subroutine outputs true, then the correct thing for my larger algorithm that I'm building to output is also true. And if that sat algorithm outputs false, then the correct thing for my larger algorithm to output is also false. Okay? If I wanted to write it in pseudocode, here it is. Transcribe K into a Boolean formula, call the sat subroutine, and return whatever that returns. Okay? Because the transcription happens in polynomial time, and because the sat subroutine, by assumption, happens in polynomial time, the running time of this algorithm is polynomial. But that's ridiculous. Circuit SAT is NP hard. It doesn't have any polynomial time algorithms. So I've derived a contradiction from my initial assumption, which is SAT can be solved in polynomial time. Another way to say this is what this reduction actually shows is a relationship between the running time of the fastest algorithm for circuit SAT and the running time of the fastest algorithm for SAT. One way to solve an instance of circuit SAT with complexity n is to spend linear time transcribing it into a formula of size order n and then passing that to an algorithm for SAT. But we believe that this function on the left is exponential. And therefore, this inequality implies that this function on the right is exponential. Okay? All right. So this is a simple example of how to actually prove that a problem is NP hard. Okay, so here's how you do it. First, I'm going to pick out a problem that I already know is NP hard. At this point, we only had one problem like that. We believe Steve Cook and Leonard Levin. We believe them that circuit SAT is NP hard. But the idea is I'm going to pick a known NP hard problem Y. Step 2, describe a, actually let me say it this way. Assume, for the sake of argument, a polynomial time algorithm for X . 3, derive a polynomial time algorithm for Y. Using this algorithm for X as a subroutine. 4, contradiction. Okay. So I picked the problem I know is hard, and then for the sake of argument, I assumed something else was easy, and then I proved that this known hard thing is easy. Wait, what did I do wrong? Oh, right, I made this assumption. And from this assumption, I derived a contradiction, so that assumption must be false. Okay. Now, what is the way this is normally said is reduce Y to X. Take a known NP hard problem Y and reduce it to this unknown problem that I'm trying to prove is hard X. Now, it is incredibly easy to get this backwards. When you want to solve a problem like, how do I get these kids to Fillory, you reduce it to a problem you know how to solve. Maximum flow. You take the problem you are curious about and you reduce it to tools you already have at hand. Okay? You build the big box out of smaller boxes that you already know. What's going on here is you're saying, there is no big box. Let's assume, for the sake of argument, there is a small box, and based on that assumption, hey, I can build a big box. Wait, I guess there is no small box either. You're reducing from the problem you know about to the problem you're curious about. And the the reverse nature of this proof is sort of mirrored by the fact that you're not trying to solve x. You're trying to prove that x doesn't have a fast solution. You're trying to prove the negation of the usual thing that you're trying to derive with an algorithm. When you're driving an algorithm, you're trying to show, hey, this problem has a quick solution. Here, you're trying to show this problem doesn't have a quick solution. And so that turns the entire argument back on upside down on its head. When we're starting out doing this at the beginning, the only known problem y I have starting out is circuit sat. But I just walked through this argument for the problem x being formula sat, otherwise just known as sat. So that means that for purposes of proving future problems are NP hard, I can start my reduction from sat. So this list over here that I'm building up on the right, this is my anti-software library. Right, when you start learning how to code in 125 and 225, you build up simple tools like, here's linear scan, here's binary search. Well, now that I know how to do binary search, or linear scan, I can do insertion sort. I can do merge sort, I can do selection sort, I can do quick sort. Now once I have sorting algorithms, then I can do other stuff. Right? And you build up this library of more and more complicated algorithms by starting it with the basics and reducing stuff out to those basics to build larger algorithms. The same is going to be true here. Once I've walked through an argument that shows that something is NP hard, it goes into my library of NP hard problems, which I can then pull out to prove that other things are NP hard. Okay. So I want to show one more somewhat non-trivial example of this idea. Because so far the examples of NP hard problems I've shown you are either magic or just notation. Okay, so circuit sat being NP hard with a couple of hours and farting around with Turing machines, I could probably convince you. There's some interesting technical details that, again, for the right value of interesting. But we can just believe that. Going from circuit sat to sat, that was really like, translating something from Java into Python. It was just a change of notation. It wasn't really talking about really doing anything significant. The problem that I want to talk about next is something called 3-sat. So the idea that may be somewhat counterintuitive is, of course, sat is hard because I can basically describe anything I want using an arbitrarily complicated Boolean formula. Well, suppose I put some restrictions on the expressive power of my Boolean formulas. I'm not going to consider all possible Boolean formulas. I'm going to consider only Boolean formulas with a very special structure. Okay, so specifically, I'm going to look first at Boolean formulas that are in what's called conjunctive normal form. So what conjunctive normal form means is that the formula is at the top level decomposable into clauses, these things in parentheses, that are connected by ands. It's a conjunction of clauses. Each clause is a bunch of things connected by ors, and each of those things is either a variable or a negated variable. Okay, so if I want to think about a parse tree for this kind of formula, what I should imagine is I have, a big and as the root of the tree, and then I have an or that's the next level down, and I might have some nots, and then I have variables. Okay. So my tree is very shallow. The formula has a specific structure where the top level operation is always anding things together, and the second level operation is always oring things together, and the third level operation is always maybe negating and maybe not. And that's it. That's all I'm allowed to do. And then I'm going to put a further restriction on this, which is I'm going to require exactly 3 literals in each clause. So this is a conjunctive normal form formula, CNF formula, but it's not a 3CNF formula. It's not an instance of 3SAT. So 3SAT, I'm required that I can't have any clauses like this that only have 2 variables, that's too small, and I can't have any clauses like this, that's 4 variables, that's too big. I need exactly 3. Now, this is really imposing a significant amount of structure on the formula. It's not actually possible to express arbitrary Boolean functions using a formula with this tightly constrained structure. This is like trying to express all polynomials, but you're only allowed to multiply once. You just can't do it. Okay. Nevertheless, I claim that this constrained version of satisfiability is still hard. Again, now I have to refer back to intuition. Normally, when you solve a more general problem, if I say, I can solve maximum flow in polynomial time, that implies in particular that I can solve maximum flow on any particular class of graphs in polynomial time. Used to thinking of special cases as something where, oh, I just call the more general algorithm. Again, we're doing things backwards. We're trying to prove that things are impossible. When I say that a problem is hard, I mean there's no single algorithm that can quickly solve every instance of the problem. That doesn't rule out the possibility that there's a fast algorithm that solves some special case. So when I'm proving that this special case is hard, I really am deriving a stronger result. So how does that stronger result work? Okay, so here I'm going to do the reduction directly from circuit sat. I'm going to say, I know that circuit sat is hard. Let me assume for the sake of argument that there's a magical polynomial time algorithm that can solve 3SAT. Given a 3CNF Boolean formula, it will tell me correctly, yes, it's satisfiable, or no, it isn't. The only thing different is this transformation is going to be a bit more complicated. Right? So the first thing I'm going to do is what's written here is step 2. I guess what is the first thing that I do? What is the actual first thing that I do? Oh yeah, I need to make sure that my gates are binary. So if I have, for example, an AND gate that has 3 inputs, I need to transform it into a small tree of 2 input AND gates. This blows up the circuit by maybe a factor of 2. You roughly double the number of wires. Okay. Then I do exactly what I did with SAT. I take for each gate, I transform that into a clause that looks like this. Okay, so I just write down every AND gate as a clause of the form A equals B and C. Every OR gate is a clause A equals B or C. Every NOT gate is a clause A or B. A equals not B. Just like I did for the general satisfiability reduction. But now I'm going to go further because those clauses have equals in them, and I'm not allowed to have equals in conjunctive normal form. I'm only allowed to have ands, ors inside the clauses. So the next thing I'm going to do is this I'm going to normalize it to make everything be in conjunctive normal form. So I'm going to replace, for example, every clause of the form A equals B, A, and C with this collection of clauses that really are in conjunctive normal form. Now, how did I derive this thing over here on the right? Those of you who are perhaps from an electrical engineering background might remember Carnot maps. Those of you who took 173 might remember exactly the same thing under the name truth table. I just built a truth table and then I wrote down a description of it in conjunctive normal form. It's really just brute force. It takes, once you realize what you're doing, it takes, 15 seconds for each of those lines. Okay, so this means now I've transformed my original circuit first into a circuit with binary gates, then into a formula that has some equal signs in it, and then into a formula that's actually in conjunctive normal form. But it's not 3 literals per clause yet, because I have a couple of these, every one of these chunks has clauses that have only 2 literals. So I need to do some further expansion. And that further expansion involves introducing new variables into the formula. So if I see, for example, a clause that says A or B, I'm going to introduce a new variable X, and I'll replace A or B with A or B or X, and A or B or not X. And you'll notice that no matter what value you give X, that small formula can be true if and only if A or B can be true. Similarly, I've actually got one clause at the very end that represents the output of the circuit that just has one variable. In that case, I'm going to introduce 2 new variables, X and Y, and then I'll replace A with A or X or Y, and A or not X or Y, and A or X or not Y, and A or not X or not Y. If the formula is, if this expression is satisfiable, if there's a way to make it true, then in particular all 4 of those clauses have to be true. But no matter what values I give X and Y, in one of those clauses, the X and Y stuff is going to contribute false, which means A has to be true. Okay. So the only way to satisfy those 4 clauses is to make A true. At this point, I've transformed my circuit into a binary circuit, into a formula, into a CNF formula, into a 3 CNF formula. And that circuit that I showed you before gets turned into this. Now, this looks horrible and ugly and big and huge, and especially compared to that nice, pretty picture I had a few minutes ago. But I want to emphasize that every single one of these steps, where I expand the gates into binary gates and then write it down as a formula, and then expand it into CNF, and then expand it into 3 CNF, every single one of those steps increased the complexity of the thing I was playing with by at most a constant factor. And I did that only 5 times. So this incredibly ugly-looking formula is in fact only, in general, about 20 times as big as an explicit description of the circuit that I started with. I'm not growing things exponentially, I'm in fact only growing things by a constant factor. And so now, if I can figure out whether this formula is satisfiable in polynomial time, that would tell me whether the original circuit is satisfiable in polynomial time, which is impossible because circuit sat is NP hard. So the only conclusion I can draw is it's not possible to decide whether a formula that looks like this is satisfiable in polynomial time, even though the formula is this very, very simple structure. Now, this structure thing is actually quite subtle. If I had said 2 instead of 3, if I could have reduced down to clauses that had only 2 literals each, 2-sat turns out to be solvable in polynomial time. So, in fact, if you try to do it, you won't. There's no way to take a 3 literal clause and turn it into a bunch of 2 literal clauses. It won't work without exponential growth, exponential expansion somehow. Okay. So starting on Tuesday, I will show you how to get from 3-sat to more interesting looking problems that don't have anything to do with logic, like independent set, clique, Hamiltonian cycle, graph coloring, things like that, that show you there really are like literally tens of thousands of these NP hard problems. Okay. Thanks.